So sorry.
Okay, so hopefully you have this filled in the middle here and it matches what I have up on the screen. Double check that this should be, if you finish this off, what you have on the screen. Tests, I'll bring the tests on Monday. So if you want to look at your tests, I gave everybody one question and then I adjusted things from there. Keep in mind, if you look at the average in OWL, it is not correct. I don't know if those stats are out there. Does it give you the high and the low and the average for the test? Okay, maybe that's turned off. All right. So test I'll bring Monday. If you haven't taken the test, makeup day, we'll do it Friday after class, but make sure you've got hold of me. Okay, well, we all start with quiz questions. So let's put this quiz up here and see where we're at. Now we're skipping, hopefully you've done some OWL maybe in chapter 7, right? You kind of got to skip around here. So maybe you went into OWL chapter 7 and did some stuff. I think 34 through 50 again is some review. And then 6 and 7 is these right here. So do we have a question on any of these? 2, okay, so for 2, what's the wavelength in centimeters of light? So here's our frequency. We know we have the speed of light is equal to wavelength times frequency. I'm doing F for frequency. We know that the speed of light is 3 times 10 to the 80 meters per second. We're looking for this wavelength, and here is our frequency. Now, frequency is in hertz or seconds to the -1, or, I mean, you could put 1 over seconds. You could draw a line like this and just put seconds down here. Now, you should be able to solve that, realize, which is why I want you to put your units down all the time, that this is in meters, but all the answers are in centimeters. Right, your answer is going to be in meters. You need to change it to centimeters at the end. Okay, what else do we have from this quiz? Yes. 4, we haven't covered 4 yet, and I haven't assigned it yet. Yeah, we'll get to 4 here. Anything else on the quiz? Anything from the review, 34 through 50? Okay, all right, so let's go back to this. Now, this actually does, chapter 7. Again, I just think it makes sense. It talks about the energy of the electron, but you don't really know where the electron is and kind of some happenings with the electron unless you go into chapter 7. So to me, it makes sense. We go to chapter 7, we talk about really where is the electron? And then we're going to go back to chapter 6 and calculate more on energy and stuff like that. So last time we did electron configuration notation. This is my cheater way to do it. There is 7 levels. Every level has an S orbital or S sublevel. Then we skip 1 to go P. We skip 1 to go D. We skip 1 to go F. We draw our arrows and then we just fill it in. We know that there is just 1 S orbital, and that can hold 2 electrons. We know that there are 3 different P orbitals, and if it can hold 2 electrons each, we could have 6 P electrons. We know there's 5 different D orbitals. If they can hold 2 electrons each, that would be 10 electrons and 7 different Fs and so on. And we know that the orbital shapes, the S is spherical shaped. These P's are weightlifting dumbbell shapes, they refer to them. The D's look like 4-leaf clovers, except for this dumbbell shape of the Saturn ring. And then F's, they're all over the place. Again, if you keep taking photographs and overlaying them, we say that there's a 90% probability, this is a probability function, that the electron is going to be within that space. And if there's only 1 electron in these, it can occupy the entire space here and there. Then we wrote out electron configuration notations. We completed the blank periodic table. And yeah, that's kind of where we left off here. Now, I want to remind you that all of these electron configuration notations are on your periodic table as a shorthand. So if we did the shorthand for calcium here, if we did the shorthand for calcium, the previous noble gas is right here. So the shorthand for calcium, that right there would be argon. So you would have argon in brackets and then 4s2. And again, these are on your periodic table. All of the electron configurations are on your periodic table. So we just looked at what was the calcium. So if we go to calcium here, try to zoom this in as best I can. And we have argon in brackets and then 4s2. Well, let's do this valence electrons. So valence electrons are, let's see, I can write it right over here. I'm going to write it and draw an arrow. So your valence electrons are your highest level S and P electrons. That's your first definition. Some will do unfilled D's and F's. Some textbooks, unfilled D's and F's. There's only one example of that. So this is our valence electrons. Typically, it's just your furthest out S and P's. So your valence electrons are the ones that are involved in the bonding. Now, if we take sodium here, and if sodium combines with chlorine to make table salt, it's probably not going to try to react with an electron way in here close to the nucleus, right? It's going to react with its furthest out electron right there. Sodium has one valence electron. What is it? It's the furthest out 3s1 electron. So these are the core electrons here. All we care about is what's going to be involved in bonding for valence electrons. It's the furthest out S. All you're looking for is the largest number. That is the farthest out, highest level. Obviously, for hydrogen, there is only one. Hydrogen has one valence electron. If we do carbon, we don't care about the 1s2. The farthest out, we get to level 2. We've got 2 here. We've got 2 here. Carbon should have 4 valence electrons. And fluorine here. 2s2, 2p5. We know that fluorine has 7 valence electrons. And magnesium, highest level we get to is 3. We've got 2 there. Aluminum, the highest level we get to is 3, right? 3. So we have 3s2 and we have 3p1. We got 3 valence electrons total. Sulfur, we get to energy level 3 is the farthest out we get. 2 here, 4 here, we get 6 valence electrons. And chlorine, two and 5, we got 7. Potassium, we get to level 4, just this one then. And if it is, if it's written in shorthand notation, you would see the valence electrons are at the end here. So 4s2. 2 valence electrons. Now, if we do iron, some textbooks are just they're not gonna do the D's at all. They're gonna look at this and say it has 2. I'm gonna split this, I'm gonna split this 2. Some textbooks are gonna include the unfilled D and say it has 8. And I blank it out. I looked this up last semester. I called the chemistry guru here that does this, and I said, what do you do? Oh, I didn't talk about D's, I was told, but we'll probably just consider that, but if you do, I don't remember an owl, I'm just blanking out if owl does it. I think owl maybe stays away from it. Okay. SE here, how many valence electrons do we have? This D is filled. We've got 4 here, 2 here, we've got 6. Krypton is a noble gas. We better have 8 noble gases. We got 6 there. We've got 2 there. We've got 8. And antimony. Highest number we get to is 5, right? Highest number we get to is 5. We have 5s2 here. We have 5p3 there. We should have 5 valence electrons. Xenon is a noble gas. We better have 8. And we do. We get to level 5, 5s2, 5p6. We've got 8. And bismuth. We get to level 6. We have 6s2 here, and we have 6p3 here. We've got 5. Those are valence electrons. Okay, furthest out, S. You're going to have S for sure, because S has to fill before P. So if you've got 1 or 2, it's only in the S. If you've got more than that, you've got some in the P. Again, all we care about is the furthest out. Level 6. Level 5. Level 5, right? Okay. We left off, and I want to go where we left off before we backtrack to chapter 6. So this is the first couple sections in chapter 7. So again, skip forward to owl if you haven't done that. Now, this page right here goes with the previous 16. So we left off right here last time, and we said that every box here is an orbital. And for hydrogen, it was 1s1. So hydrogen has 1 electron. Now, where's that electron going to go? It's going to go in the 1s, right? Now, we actually use an up or a down arrow for how the electron acts in an electric field. This electron's actually spinning counterclockwise. It points up, but we don't know which way it's going to spin. That could be spinning the opposite direction. You could put this down. Again, the electron, it's just like a basketball, right? You throw, everybody's probably tried spinning a basketball on your finger. You can either throw it up clockwise and try to spin it, and then you go like this, or counterclockwise. The electron's the same way. It's going clockwise or counterclockwise. And if you have 1 electron in there, you don't know which way it's going. You're going to have an up or a down arrow. And I just do that to know that it could be down. Now, we're going to go to carbon. So carbon is 1s2, 2s2, 2p2. So 1s2, 2s2, 2p2 from the previous page. Okay, we know that if there's 2 electrons in the same orbital, they're going to be spinning the opposite direction. So for the 1s2, we go 1 up, 1 down. And don't get ahead of me now. Don't get ahead of me. Don't get ahead of me. For 2s2, we've got 1 up and we've got 1 down. That's my 1s2, 2s2. They're going to be spinning opposite direction. Makes it all more stable. Now I've got to do 2p2. I have 3 p orbitals that I can put these 2 electrons in. I don't know where they're going to be. I know they're not going to be paired up. Okay? Because of Hund's rule. which we're going to put up here. Hund's rule basically is this. I'm going to shorthand it out. One electron in each orbital of the same spin before pairing. Maybe I can put it that way pretty good. One electron in each orbital of the same spin before pairing. And I'll do some examples of that. So Hund's rule, one electron in each orbital of the same spin before they pair up. So let's do this example. If we have P2, there's my three p orbitals, right? Px, py, pz. So Hund's rule just says this. I need to put two electrons in there of the same spin, and I don't know where they're going to go. It might look like this. This is the easy way to do it. I'm going to put one in the first one. If I put one in the first one, I don't know where it's going to go. But I know as soon as this one's spinning, I put an upward spin on it like this. I shouldn't say that. It's a counterclockwise spin. I know that my next arrow has to go up. It has to be the same spin, going the same direction. It could be in this one. It could be in this one. We don't know. Both, there could be one arrow in this one and one arrow in this one. We don't know where they're going. They could be an arrow down and an arrow down. Just so that you can look at your neighbors and compare, we'll just do the first two. So P2 would look like that. If you have D5 for Hund's rule, 1, 2, 3, 4, 5. We have 5 boxes. You are going to put one electron. If you got 5 electrons to put in here, you're going to have 5 up arrows or 5 down arrows that have to match. One electron in each orbital of the same spin. So we go like this. It has to look like this, where they're all up, or they'd all be down. But they got to be the same, right? So that's what we mean by Hund's rule. You have to put one electron in each orbital of the same spin before they pair up. Now, if I have something that ends in D6, I'm going to have to put a down arrow, correct? Which one it goes in, I don't know. Just for simplicity, what I like to do is I'll put it in the first one, because if you take your paper, oops, and hold it up to the light, it should match up somebody else's. All right, so let's go back here. My 2p2 then, I'm going to put one up here and I'm going to put one up there. And then I know that these have to be the same. By same, I mean they're both pointing up or they're both pointing down, right? That has to be the same spin. If we go to fluorine, fluorine ends in 2p5. So I'll just put 2p5. The next one is fluorine, ends in 2p5. We'd have one up, one down. Now, if we practice the way Hund's rule does this, I'm going to put 3 up first. That would be 2p3, right? I could start with 3 up or 3 down for 2p3. Now I gotta put 2 down. You don't know where they're gonna go. For simplicity, we'll do this. And I just do this, just telling myself, that could be pointing down, right? If we started all 3 going down, this could be pointing down. Well, that's how we fill this up. We just keep going the same way. So let's saddle up the horse, the bigger horse, I should say. Let's go down to 15. We're gonna go down to 15 down here, way at the bottom. So in 15, we got to go all the way over to 5p6, and I don't remember if I have these in the right order, but here's my 1s2, 2s2, 2p6. If you want to start doing it the way Hund's rule is, it'll look like that. And my yellow here is 3s2. And it might be a good idea to take the staple out if you have these stapled and go back and, because you have it right here, right? From the previous page. Then we've got 3p6. This yellow is a 4s. 4s2 after 4s2. Then 3d10. Starting to speed up, 3d10. Okay, after 3d10, 4p6. I do have these in order so far. 4p6, starting to look ugly here. 4p6. After 4p6, 5s2. This is my 5s2 in yellow. After 5s2, 4d. So green, my green section here is my D. For D10, after 4d10, 5p6. And my blue section here is my P's. 5p6, and that's it, huh? 5s2, 4d10, 5p6. Yes, that's where it ends. So now you'll see in OWL and on the take-home quizzes, you'll see this arrow diagram. And one of the arrows, they're just electrons. There should be no more than 2 in each orbital. Make sure they're spinning opposite directions. Okay. And they would probably call this orbital box diagrams. Orbital box. Each box is an orbital. Okay. And again, this is Hund's rule, right? That those are pointing the same way. It looks like on the last one, I could not fit this. So on the last problem, this is my 4D. I just couldn't get this to fit. So on the last problem, you're going to need this. Let's just fix it here. You're still going to need a 5D. And you're going to need a 6P. We'll finish the last one. Okay, let's give chapter 7 a break. Let's backtrack now to chapter 6. Backtrack to chapter 6, but you have an idea of where the electrons are, what can happen to electrons. So now we can backtrack to 6 here. So previously, we started out saying that the higher the frequency, the higher the energy, the shorter the wavelength. So now you're going to actually see that come out into some calculations. And I believe then we should be on page 6. Okay, so on page 6, it is actually Planck that comes out with our equation that relates. I'm going to change this frequency to an F. And Planck's equation says that our energy is equal to the change in levels. It's a Planck constant times the frequency. Now this N now is change in energy level. N is just energy level. And I'm going to change this to an F here. So now you at least have some idea about energy level. That's why we went to chapter 7, talking about energy levels. Now we're coming back. Where triangle meets change, N is the change in energy level. If the change in energy level is 1, which means the electron moves up 1 level or down 1 level, there is a change from one energy level to the next lower one, or it can go up. Frequency. I'm putting F is the frequency of the wave, and H is a constant that came to be called Planck's constant. H, 6.626 times 10 to the minus 34 joules times seconds. That is energy in joules. Now, Planck proposed that the energy is quantized. Quantization means only certain energies are allowed. It has to be at a certain energy level and not between. It's like this, the rungs of a ladder. You cannot step between and go up. You have to be on a certain rung. The electrons have to be at a certain energy level and not in between. Well, along comes Einstein. Einstein expanded on Planck's work to explain the photoelectric effect, which you're going to see on the next page. Einstein proposed that light to be massless but particle-like, and he referred to them as photons. A photon is a packet of light of discrete energy. Photons strike atoms on the metal surface, causing electrons to be ejected only if the photons have high enough energy. So I'll go to the next page. And I just have a diagram of this. So this is the photoelectric effect. If we have light coming in and hits this metal surface, nothing happens. We're looking, this is a switch, okay? This is a photocell. We want electrons to come to this anode right here. Unless this frequency increases enough, higher frequency, higher energy, right? It hits this surface, it will eject electrons. If you turn this up more and get higher intensity light, you're going to eject more electrons. That is the photoelectric effect observed by Einstein. But you have to have higher frequency light to do it. Therefore, the higher the frequency, the higher the energy. And we can see that this meter obviously higher than this one. Well, what is the relationship here? So here's our beginning equation of Planck. But if we substitute in frequency here, from this, we've already worked with this equation, right? C is equal to lambda F. And if we solve this for frequency, it would be the speed of light divided by the wavelength. Let me highlight this here. This pink here. Frequency is just speed of light divided by the wavelength. So we can just substitute it in right here, right? We just substitute that in. So now, if you look at this equation right here, you know that energy is equal to the frequency, right? It's proportional to the frequency. If I just look at this much, this is what I've been talking about. The higher the frequency, the higher the energy, correct? The equation tells it to us right there. But when you substitute this in, what about the wavelength? How do you make this fraction the greatest when this wavelength is the lowest, right? So this is what I'll quizzes you on over and over and over. Looking at the first part of the equation, as frequency increases, energy increases. Looking at the second part of the equation, as the wavelength decreases, energy increases. That again is what we've been talking about. Okay, so let's get to where an owl type equation, and I've got an owl question here. Compact disc players, now obsolete. I think everybody in here has seen a CD, yes? How about a VHS tape? VHS tape? The day's coming though. Okay. So CD player uses lasers that emit red light at a wavelength of 685 nanometers. So this right here is 685 times 10 to the minus 9 meters, right? All right. And I should go up here and look at these units here. We know the speed of light is in meters per second, right? This is 3 times 10 to the 8 meters per second. This is Planck's constants in joules per second. Well, we want to keep our wavelength in meters. Our energy we get is then joules per photon. Okay, what is the frequency? Or what is the energy? I'm sorry, we're looking for energy here. And let's go to our equation. We have E, our energy is equal to Planck's constant times the speed of light divided by the wavelength. We're given the wavelength. And Planck's constant, we can go 6.626, that'll get us 4 sig figs, times 10 to the minus 34, joules times seconds. Speed of light 2.99, or should be safe to round this to 3. I should do the 7 maybe, but 2.9998. We're good. I should put 3.000 meters per second. We're going to divide by our wavelength. 685 times 10 to the minus 9 meters. Now, when we get all done, it wants this in kilojoules. So to get this into kilojoules, we've got a joule up here, right? So we can go 1,000 joules down here, 1 kilojoule. We should get for that. Make sure you're not putting in times 10 in your calculator. You should take this number times this number, hit equals, divide by this number, divide by 1,000. Hit your division key twice, right? Do not go divide by 685 times 10 to the 9th times 1,000. That does not work. It flips 1,000 back up. Hit your division key twice. Grab your calculator. Everybody's having a good day when they're using their calculator. Everybody's a winner when they're using their calculator. Try this on your calculator. Did we get to the minus 22? All right, so we've got 2.90 times 10 to the minus 22 kilojoules per photon. Yes, somebody else did that? Yes, okay. All right, here is an owl question. I put not so ugly owl. I'll tell you when the owl is ugly, because I'll put ugly owl on here. This one's a not so ugly owl, but and this is straight out of owl. A local AM radio station broadcasts an energy of, and notice it's in kilojoules per photon. But Planck's constant is in joules, so we're going to fix that up. Calculate the frequency at which it is broadcasting in kilohertz. All right, so write down what we got here. We know that our energy here is equal to 4.96 times 10 to the minus 31 kilojoules per photon. Now let's change that to joules. So if we do this, we would go 1 kilojoule down below, 1,000 joules. Well, let's see, we just need a frequency. And yeah, we just calculate this out. So we're going to use the first equation. We're just going to use E is equal to Planck's constant times the frequency. And we're looking for our frequency. So we can take this energy right here and divide by Planck's constant. So this, I'll do it right here. So this part right here is oh, we could just add it to it right here. There's our energy. Let's just divide by Planck's constant. Because we want our frequency. Let's just put our line in right here. If we divide by Planck's constant, which is 6.626 times 10 to the minus 34. What do we get out of this calculation? I've got 7.4. We can fix this up, talk about sig figs, but if I write the whole thing down, I got 8.566. Anybody else get this? Okay. So this is in hertz. But we want it in kilohertz. And what do we got for sig figs out of this? We got 3 sig figs, so I'm going to pull this down here. And I'm going to go 3 sig figs, and I'm going to convert. So if I do 3 sig figs on this, I'm going to go 749,000 hertz. And 1,000 hertz in 1 kilohertz. So we would end up with 749 kilohertz. Make sure you try this with your calculator, right? Make sure you are trying these with your calculator. Okay. Photoelectric effect again. I'm going to put on one video here. Make sure I share the screen correctly. And see if I can do it. Yes, but I've got to share this screen again. So give me a different screen. Oh, where did my thing, my controls go? Oh, right here. Yeah, thank you. Let's see. All right. This is not law. This is the one I want. Yes. There are some good videos here linked. Let's see if it's going to play. Come on. Oh, it's up here.
What do you see? You see white light. Now, where did white light show up on our electromagnetic spectrum? It wouldn't anywhere. So what is white light? We can see it, certainly it's visible light. White light is simply a mixture of all the visible light, all of the visible frequencies of light, everything from red up to purple. That mixture gives us white light from the sun. It's just the full electromagnetic spectrum of visible light and beyond, certainly. Now I have a flask here that contains, we'll call this our sample, but it actually is just water in this case. We'll put that right in front of the light bulb so you can see it here. And now, what do you see? You should still see white light. The white light is being transmitted through the sample. In this case, you're the detector. In this case, you're seeing the full white light spectrum come through. Now, finally, I'm going to take some green food coloring, and I'm going to simply add it to our sample. And no great shock to you. I'll mix it up. It turns green. So once again, I'll ask you, what do you see now? I mean, if you could look at the wavelengths of light coming to you, what are you seeing? Clearly the chemical in the green food coloring is doing something. It's changing, it's interacting in some way with the light that's transmitting through the sample, so that you're no longer seeing white light, you're not seeing the full visible spectrum then. Well, what are you seeing? Is it in fact that the food coloring is blocking green light? Well, if it was blocking green light, it wouldn't look green to you, right? That would be missing, and so that would be the one wavelength that you wouldn't be seeing. So what it must be doing is blocking all the other colors, or at least most of the other wavelengths of light, so that the dominant thing that you see is green light. In fact, what it could be doing, and is likely to be doing in some cases, is if it blocks out the complement to this color, the complement to green is red, your brain actually will perceive the opposite. So in other words, when your brain sees the absence of red light, it thinks it's seeing green light. You can actually do this at home if you draw a big, for instance, if you draw a big red spot on a white piece of paper and you stare at that red spot without moving your eyes for about a minute, then quickly look away and let your eyes refocus on the white paper, you'll see the opposite color. You'll see a green dot. Your brain will perceive the absence of red because you will have saturated your red receptors. And so you'll actually be seeing a green light then. And that's what's going on here essentially. We're absorbing other frequencies, in particular the complement of green light, and so you see the green light come through at you. What I'm describing for you is an absorption experiment. The light bulb would be what we would consider the source, usually a full spectrum, either the visible spectrum or sometimes in the ultraviolet or in the infrared spectrum. A sample, in this case just our water and food coloring, and in particular the molecule that we're trying to probe. So this is a great way of probing what's happening in a molecule. We're putting the molecule in, passing light through the molecule, and looking, you are the detector in this case, looking at what wavelengths come through on the other side. So let's talk about this a little bit more. An absorption experiment is one of the most fundamentally important ways a chemist can probe atomic and molecular structure. Let's review a little bit what we just did. Once again, the idea of absorption is we pass white light through a sample. The white light initially contains the full range of colors. The sample then absorbs some of those frequencies, leaving only specific frequency to the sun, for instance, wavelengths, and we need to divide it now into the different frequencies or the different wavelengths again of light. So we can use a prism, which causes the light to bend to a differing degree depending on what the wavelength or frequency is of the light. Light, our sample, in that attempt to turn this on so you get a better view. You can see this beautiful purple color. Clearly, this is different than the tungsten light bulb in that we're not seeing white light now. We're seeing what looks.
We'll look at some of those colors, calculate some of those colors out next time we meet on Friday. Please, please, please go into chapter 7, work on what you can. I'm sure chapter 6, deadline for chapter 6 is going to change because I think it's on Sunday maybe or something like that. So the chapter 6 and 7 deadline and will probably be the same time. Thank you. Roll sheet.